Welcome to Lesson 1B, Volume Flow Rate. Let me start with some notation. We're going to use Q as the volume flow rate, and I'm sure if you've taken fluids, you've seen this other convention, which is V dot, V volume, and dot mean volume flow rate. That one makes more sense. That's the one I use in my fluids book, but we're going to use Q because that's more popular for air pollution. People that study air pollution use Q, so we will use Q for this course. So typically we're talking about flow through some kind of a duct or a smokestack if it's vertical, and we have some cross-sectional area, A or AC, cross-sectional area, and then we'll have a velocity profile. This is almost always turbulent, not laminar, so I'll draw a turbulent profile. So this is the velocity profile. This is the bulk air, and there will be some average U or V. We sometimes use V for velocity. I'm going to use U here as the average velocity, or average speed actually, since it's not a vector, through the duct. And so we will define then this volume flow rate as U times the cross-sectional area, AC. So this is just a review from your fluid mechanics class. As I always like to do, the dimensions of Q are volume per time. And in terms of primary dimensions, L cubed over T. And then the units of Q can be many different things: meter cubed per second, cubic feet per second, cubic feet per minute, liter per minute, etc. So you take your choice of all those different units. There's some special cases, such as CFM, which is cubic feet per minute, or feet cubed per minute, which is commonly used in the HVAC industry and with air pollution studies, and LPM, liters per minute, is also popular if you use metric. Unfortunately, this air pollution business is a mix of English and metric units. So we'll do both as necessary. There's a difference between what we call standard and actual volume flow rate. So I want to make sure that you understand that difference. By definition, actual volume flow rate is the volume flow rate based on the actual, as the name implies, actual temperature and pressure of the gas. So basically for a given M dot through the duct. So this may be a round duct or a rectangular duct, but there's some M dot flowing through there. So M dot is rho times Q, and Q is then M dot over rho. And the problem is that for a given flow rate or mass flow rate, this density changes with temperature and pressure. So we're going to define the actual Q, as I said here, based on the actual T and P in the duct. And there's really not anything special about actual Q. I'll give it in English units, commonly used feet cubed per minute, or CFM. And there's a special unit in the English system is ACFM, meaning actual cubic feet per minute. So you might write, for example, Q equal 328 ACFM, and people understand that to mean it's the actual cubic feet per minute. In metric, it's not quite so simple. We typically use meter cubed per second or liters per minute, etc. And there's no special unit. So we would have to write this as Q equals, say, 6.21 meter cubed per second actual. You would write the word actual there to indicate that this is an actual volume flow rate. So all of that is typical of what you've done in fluid mechanics, so nothing new there. What may be different for you is this so-called standard volume flow rate. This is a hypothetical volume flow rate equal to what the actual flow rate would be at some standard temperature and pressure of the gas. So the actual flow rate is based on the actual temperature and pressure of the gas, but we would pick a standard temperature and pressure. So M dot is the same for either case. So you have your duct and you have your M dot flowing through it. So how do we express this standard Q? We want to express volume flow rate in some kind of standard way. So in other words, we choose a standard temperature and pressure. And there's different ones you could use. And we're going to use typically what we call standard ambient temperature and pressure. But before I get to that, I also want to mention that M dot is rho Q for either of these cases, but the Q will depend on the density, and the density depends on temperature and pressure. So for a given M dot, if we define temperature and pressure as the actual, we'll get some rho. If we define it in some other temperature, some hypothetical temperature and pressure, we'll get a different row. That's why these two Q's will be different from each other. So again, in English units, we would have feet cubed per minute equal SCFM equals standard. The S stands for standard cubic feet per minute. So again, you would write Q equal some value 121 SCFM. In the English system, in the metric, again, there's no special units. So if we did liter per minute, we would write Q equal 4.16 or meter cubed per second or liters per minute, and we would write that standard. You'd have to write out the word standard. This is one place where English system has one benefit, and I hate the English units, but this is one place where it's kind of nice because you have ACFM and SCFM defined. Okay, why do we care about this? Why would we use it? Let me give you a good example, and that would be natural gas to your house. So there's a gas line. If you have natural gas that comes into your house, and you pay a certain amount of dollars for the mass, you actually pay for the mass of natural gas. So the actual mass flow rate is what we want. The problem is the density changes for different houses. So you have this gas line and it branches off to one house and it branches off to other houses. So here's your house, here's your neighbor's house. And if you're on a different portion of the line, your density would be a little different than his, and therefore you would have a different actual flow rate, but you want to pay by mass. So what they do is give you a standard cubic feet per minute or standard meter cubed per second of the flow rate, and then you can actually pay the same amount of dollars for the same amount of gas. Otherwise, it would not be fair. Here's the main equation for any standard temperature and pressure. You can convert to Q standard equal Q actual times P over P, and this can be PSTP, typically atmospheric pressure 101.325 kPa, and then TSTP can be, depending on if you're a chemist or some other kind of engineer, there's all kind of different TSTPs. I've seen 0, 15, 20, and 25. For air pollution, we always take SATP. So when I say standard, we're talking about the standard for air pollution is SATP. So standard ambient temperature and pressure, and these are defined as follows. So I'm actually going to erase this one, and this is what we're going to use in our class. You're going to use standard atmospheric temperature and pressure. And I just want to make a comment here that you always use absolute temperature and pressure. Never use temperature in degrees C when you do equations like this. It will not be correct. Never use gauge pressure. You use absolute temperature and absolute pressure so that you don't make a mistake in your calculations. All right, let's do some examples. Here's an example of James measures the volume flow rate of air in a lab experiment. The flow is labeled, the flow meter is labeled standard flow rate, but he needs to know the actual flow rate, volume flow rate. So he measures with his instrument the standard volume flow rate, the temperature and the pressure, and his flow meter says it's based on 25 degrees C and standard atmospheric pressure. Notice that the pressure is the same in almost all these standard. It's only the temperature that is a variable, but here it is SATP, standard atmospheric temperature and pressure, 25 degrees C and standard atmospheric pressure. So how do we calculate the actual volume flow rate? Well, we plug into the equation. By the way, all these equations are on the equation sheet, and I recommend that you refer to that a lot as you're doing homework, as you're taking quizzes. Get familiar with where everything is on that equation sheet. It's in roughly the same order as we present the material, and I'll keep modifying that as we go through the semester if necessary. So here's our equation, and what we'll do is we'll solve for what we want, which is Q actual. So we can solve that equation, and we get this equation for Q actual, which is what we want. I have a comment here. Again, some of you just want to plug in numbers immediately. Please get into the habit of going as far as you possibly can in variables before you plug in any numbers. That will save you a lot of trouble in your life in the future. Sometimes nice things happen, like certain variables cancel out. Also, you won't make as many mistakes if you're trying to write down intermediate steps or save them in your calculator, recall when you hit the wrong button or something. So I like to do everything as far as possible in variables, and then we plug in the numbers at the end. So when I plug in the given information, which is the standard Q, we have the temperature and pressure, and we want to just plug in this equation. So let's do that. We'll plug in all our numbers. So here's what all the numbers look like when I plug in, and notice that I had to convert to K. You don't want to ever put 40.5 degrees C. We have K, and notice that the units cancel here, and so we're left with meter cube per second, which we can convert to other units if we want. And so when we plug into our calculator, we get Q actual equal 1.519 meter cube per second. And in general, in this course, and typically for engineering, you give your final answer to 3 digits. You can look at the actual amount of significant digits in each variable, and here I have 3 digits everywhere, so that's appropriate. So Q actual, my final answer would be 1.52 meter cube per second. Let me talk also about mass flow rate. I already mentioned that m dot is equal to rho times Q, and Q is UA or UAC, so it's rho times U times AC. So that's our definition of m dot, and you could pick either a actual or a standard, but remember what I said before, the density and the Q are kind of independent because the density is based on temperature and pressure. So if you're using actual temperature and pressure, you'll have an actual rho and an actual Q. If you're using some standard like SATP, you have a different rho and a different Q, but your m dot should be the same because that's what's actually flowing in your duct, and that doesn't change whether I describe it in actual or standard flow rate. So the m dot, there's really not a difference between standard and actual. It's the same mass flow rate, independent of whether you use Q standard or Q actual. And I want to also point out that this is what we call the bulk or total mass flow rate, and that means it's of the bulk air. I like the word bulk better than total. Both mean the same thing. It's the bulk air, and that bulk air would be air plus some contaminants. Usually, if you have flow going up a chimney or in a duct in some kind of a plant, there's vapors in there of some chemicals, some air pollution components. There may be more than one, but generally it's mostly air. It might be 99% air, and then the rest is some kind of contaminants. So it's mostly air. That's typically your biggest component. That's not always the case, but typically that is the case. Sometimes when you have combustion, you have some very large amounts of contaminants in the exhaust. That's not mostly air. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.